Welcome! Today we are going to talk about phase diagrams. So phase diagrams are a way for us to look at a comparison of pressure and temperature for a different substance along different points. So let's draw a graph. You're going to want to draw a graph. You have room on the next page. Give yourself plenty of space because we're going to add quite a bit of things to our graph. So you're going to want to draw an XY axis, and on our Y-axis we want pressure, and on our X-axis we want temperature. Go ahead and get that set up. And I will set up my graph and then show you what it looks like, and then I'll let you just copy it down. Give me a second. Alright, so this is the graph that I want you to draw down, and we're going to add things to this. So make sure you take a second, pause, draw it just like this. You want kind of the same shapes. And we'll talk about what this graph means. So most of the time when you're looking at a phase diagram, you won't usually have to make your own phase diagram. You'll just have to interpret information from a phase diagram. So let's talk about what this phase diagram means. The phase diagram, we're going to kind of bounce back and forth because the words below describe the graph above. Each line represents temperature and pressure at which two phases may exist in equilibrium. So even though those are kind of curves, those are considered lines. So for example, if we're looking at this phase diagram, it's almost like it's broken up into regions. Everything in this particular region that's between the A and the B. So if we think about something that is at a low temperature and a high pressure, those things are often solids. So I'm going to label these with a different color. I'm going to label them with this light blue. These are solids. So anything in that A, B range. And then if we have something that's at a kind of middling temperature and middling pressure, all of these things in this region are all liquids. So anything between B and C. And then anything that's at a high temperature and a really low pressure, all of those things are going to be considered gases. So it's kind of split up into regions, like I said before. Now we have a very special point on this graph. It's this middle point in between. You might notice that point D. That's what's represented as what we call the triple point. So I'm going to circle that point there. I'm going to make a little line here. I'm going to call this the triple point. The triple point is the point in which everything exists in the same time. So that's the next blank in the notes there as well. So the triple point, again, is the point in which solids, liquids, and gases exist all at the same time. It's a very unique point. It usually requires a very specific temperature and a very specific pressure. It's probably not something that you've ever observed. But the lines themselves represent points in which those things exist in two separate phases. So in other words, line A, the line A that's between solid and gas, on that line is everything that exists as both solids and gases at that specific pressure and temperature. Anything below is a gas, anything above is a solid. Line B is the same way. It's everything that exists as both a solid and a liquid. And line C is everything that exists as both a liquid and a gas. And again, if we shift in any direction, we go into that phase. But those lines kind of represent the middle point, the split between one and the other. Okay? So the normal boiling point may be determined by drawing a straight line at 1 atmosphere. This is a bad blank. There's no reason for that to be in your notes, so just cross that out. Horizontally along the diagram. So let's go ahead and go add 1 ATM to our graph and then interpret that after we have it down. Let me show you what I mean. Okay, so if I have 1 atmosphere, as you can see as I drew it on the graph, I have a point at 1 atmosphere. If I go horizontally along the line until I hit the line that represents the difference between solids and liquids and I go straight down, then at that point I would refer to that as my normal melting point at 1 atmosphere. It's like a standard. And then if I keep going to the line C, which represents the difference between liquids and gas, I go all the way down. That's my normal boiling point. Because think about it, like what does it mean for something to go from a liquid to a gas? Well, it's either evaporating or it's boiling. But based on this line, I have like a bunch of different points that I could consider a boiling point. So I have to consider like a standard. And the standard is at a specific pressure, which I call 1 atmosphere. Okay? And let's keep going. So sometimes we have different phase diagrams that have different slopes. say for example, if we have a phase diagram that has a negative slope on its liquid solid line, right? So we're not talking about a negative slope across the whole thing. We're talking about a negative slope along its liquid solid line. So let me show you what that looks like in a very small little graph. You can add this onto your thing if you'd like, but let me go ahead and show you an example. In these graphs I have here, I've represented the solid liquid equilibrium line in pink. So as you can see for the first one, I have a negative slope. And that negative slope means that the liquid phase is more dense than the solid phase. This is actually something that's really unique to water. Water becomes more dense when it goes from a solid to a liquid. Whereas most other substances, I can't even really think of another example besides water, most other substances are going to have a positive slope on their liquid to solid phase, which is represented by that second graph. That means that when they go from a liquid to a solid, they become more dense. Honestly, usually the thing that occurs, a basic trend, is that when things have enough pressure applied to them, they will form their most dense phase. This is the truth also with water. If I have an ice cube and I apply pressure to that ice cube, it will start to melt. It will not freeze like other things. Other substances, if I have them and I start pressurizing them enough, they start to form a solid. Liquid, however, not liquid. Water, however, does the opposite, where it turns into a liquid. And that's based on its phase diagram, which is good for us because that means that ice floats and we don't have a bunch of water at the bottom of the ocean that's frozen, and every big thing would be bad. Our whole planet would be different. So we're glad that water is more dense than ice. And that's it. That's phase diagrams. So remember that with a phase diagram, you just have to be able to really interpret the values on the graph. So when you see a phase diagram, you should be able to point where the triple point is. You should be able to identify normal melting, normal boiling by identifying where that 1 atm is. You should be able to identify the different regions, solid, liquid, and gas, and what the lines mean, right? So like the lines interpret the difference between, or all of the points in which we are transitioning from a solid to a liquid to a gas, or a solid to a gas. And that's pretty much all it takes. So it's really just interpretation. And that's it, folks. We'll see you next time.